Alrighty, and let me go ahead and share my screen then. Okay, cool. Can everyone see the USACO site? Yeah, okay, cool. So let's start with the first problem. Comfortable cows. So in this problem, we're given a grid, a 2D grid, and Farmer John is going to add some cows to this grid, and he'll add them to a certain cell. And so they define this term comfortable. A cow is comfortable if they are horizontally or vertically adjacent to exactly 3 other cows. And so Farmer John essentially wants to add cows until no cow is comfortable. And so essentially in this problem, they just want us for each eye out of all these cows. We need to say how many cows will we need to add until there are no cows that are comfortable, starting with only the first eye cows. Okay. So does anyone have questions about what this problem is asking? And I can also, let me pull up the whiteboard. So essentially, like, we're given this grid. We're given this grid. And cows will be placed in each cell. Right. And they and they define cow to be comfortable if it is horizontally or vertically adjacent to exactly 3 other cows. So like if my middle cow is the cow we're considering, I'll make it red. If the middle cow is the cow I'm considering, then this cow would be a comfortable cow, right? Okay, cool. And so how do we make this cow uncomfortable? There's only one way we can make this cow uncomfortable now. It would be great if this can be interactive. I want you guys to participate a bit, but I can answer this one. So to make it uncomfortable, like we must just add another cow below it because we can't remove any cows, right? So the only way to make it not exactly 3, we would have to add a 4th cow. Okay, cool. So that's the problem. And so I guess they also have this twist of like we need to answer this question of how many cows we need to add to make sure that no cow is comfortable. But they have this twist where it's like we want to do this for every like prefix of cows. So every for every like yeah, so literally just a prefix. I don't know if people are familiar with with what a prefix is, but just to be extra clear, like if we have these cows, I don't know what I'm doing. Like if we just like have these cows, then like an ith prefix would be like the first I cows. And so if only these I cows were placed on the grid, how many cows would we need to add to make sure that none of them are comfortable? That's the question. Okay, cool. So does anyone have any ideas on how we can tackle this problem? Either if you did it already in the contest, or if you, or just like now based off what we're talking about, any ideas on what to do here? Oh, there's a chat. Let me open this. Yeah, and Alex, feel free to share your idea with general. Can you guys message in the general chat? You guys don't have to DM me. But yeah, so Alex's idea was basically to run through each active cow to see if it's comfortable. Cool. And so I guess when you say active cow, what do you mean by that? Present cow. So I guess, sorry, the reason I'm asking is because since we do want to answer this for every single prefix, are you talking about for a specific prefix or like for every cow, like all N cows? And okay, yeah. That's fair. And you can also feel free to just chime in, Alex, if you want to try to explain it rather than type it. But actually this raises a good point, right? So this problem added this twist about like we need to do this for each prefix, which if we just think like in a very standard way of how we would answer this for each prefix, you can imagine we have a solution that answers it for a given prefix. So then to answer it for every single prefix, we could just apply our solution to every prefix, right? That's like probably the most standard way that we could handle this whole, we need to answer n queries. But obviously that'll probably discount a lot of our solutions given that n is 10 to the 5, right? Because if we apply our solution to every single prefix, we'll be adding like a factor of n to our complexity, right? So our total complexity would be O of n times like whatever our solution is, whatever our solution's complexity is. So this probably like limits what we can do, right? But here's actually where I'll say wrong. So in problem solving, it's all about getting from the problem to your solution along some path, right? But the steps you need to take aren't very clear. And so at every step, you never want to kind of limit yourself to not doing something, unless I guess it's always hard to say absolutes, but in general, you don't want to limit yourself. So here I kind of mentioned if we apply our solution to every prefix, then our solution has to be quite fast. In fact, like what can't our solution be, or what must it be for this complexity to work? Let's see. Less than n, exactly. Right. So if our solution is anything linear or slower, then this whole thing would not pass the time limit. So yes, our solution would have to be sublinear. Now, why is that like almost completely infeasible in order to do? Like why is it almost definitely impossible to do this in sublinear time? Or I guess like at first glance. And so maybe this isn't that obvious to see, but it is a very common way of thinking. But we have to read in the input, right? And so if for every prefix we're reading over, we want to solve this problem kind of in isolation, then we have to read through the entire input, and so that by itself just takes linear time. So that's why this certainly wouldn't work if we were doing every step in isolation. So maybe this starts to give us some ideas of, okay, we know we can't do it in isolation. We need to maybe reuse some information as we go from step to step. But regardless, the whole point I was trying to make was that let's never limit ourselves to blocking off any ideas this early on in tackling a problem. So what we can do instead is just ignore this for now. As you'll find, when you solve problems, it's always easy to ignore constraints or ignore things that make it hard, just so you have like a starting point. So let's just ignore the fact that we have to solve this problem for every prefix, and let's just try to solve it for a given prefix. So let's just say, or we'll just solve it for all n cows. So let's just say that you're given n cows, you only need to output what is the minimum number of cows needed to make sure no cow is uncomfortable. And let's just try to tackle this problem. So now if we go back to Alex's solution, there's not really any confusion about what is an active cow, because there's no prefix idea. So now we can try to run through each cow to see if it's comfortable. Okay, so yeah, I mean, this makes sense, right? Because we do need to check if a cow is comfortable or not. So let's say like we run through the grid, right? How big is this grid again? Okay, 1,000 by 1,000. Well, it could be longer, but initially it will be. Regardless, yeah. So we could run through each cow, and let me put these cows here. Let me draw that with an X, right? So let's just say that there's like cows here, here, here. So we run through each cow and check if it's comfortable. Okay. So in this grid, which cows are comfortable? And I guess it's hard for you to tell me, but let me know if I'm making any mistakes here. I think this cow is comfortable. This cow looks comfortable. And I think that's it. I think those are the two comfortable cows. Remember, they have to look something like this, where it's one cow and then in the adjacent cells only, not the diagonals. There's three cows adjacent to it. Okay, so let's say we've run through all the cows. We found that these two cows are uncomfortable. What next? So obviously we need to try and make them uncomfortable, right? Let's see. Yep, we have to make them uncomfortable. You have to add cows to the remaining empty slots, add cows to make them uncomfortable, and check the new cows too. Okay, yeah, this is all good. So we definitely need to make them uncomfortable. And so the way we can do that is, like we drew over here, add a cow to the remaining open slot. So in this example, we would like add these maroon cows here. And I guess here there's actually, oh, so sorry. Yeah, it's an unbounded grid. So there is like space here. I just didn't expand the grid, but it's like an infinite board. So we would add a cow there and there. And then Alex made the point of, we also need to check to make sure that these new cows aren't comfortable. Because let's say this is a bad example, but let's say that there was actually another cow chilling out over here. Well, this maroon cow down here is actually now also comfortable. So we need to kind of ensure that this cow won't be comfortable as well, which would then lead us to needing to add another maroon cow here. And I guess this cow is also comfortable, and so on and so forth, essentially. But yes, okay, so this solution is making sense. And so the details of the implementation aren't too important yet, but one thing that we might want to think about is how long would this process take? Because right now what's unclear to me is like, okay, when will this process ever terminate? If we're doing this check where on the new cows we need to make them uncomfortable, then what's preventing this thing from going on for a really long time? Just like this kind of manual checking and greedily filling that process. Do we have kind of like a bound on how long this might take? Any ideas? Yeah, and so I think it's a bit tricky to see, definitely. But but I guess so. How can we think about this? So oftentimes it can be useful to think about the extreme worst case of what can happen, right? So in the worst case of what can happen, we're adding these new cows, and they keep on needing more cows to be added. But let's think about specifically what is like the mechanics behind this. Like, in what scenario would we actually need this process to happen? So you can imagine, like, there's some argument that can be made, and I won't go into the details here because I think this is a good experiment for you to think about on your own. But essentially, one trick you can do is like think about the number of cows that are needed to exist in order to cause like another cow to be uncomfortable. And so kind of what I mean by that is like, in order for a cow to be comfortable, it must have like 3 other cows already surrounding it, right? And so they give us this bound on how many cows there will be to start. And so what you can think about is if you're only adding, like, for every set of 3 cows, you may add 1 new cow, right? But in order for this new cow to then also be uncomfortable, you need another kind of 3 cows, right? Because it only has 1 guy above it that's like filled in, right? So like basically you can make this argument that you're adding cows like slower than the rate at which they're being used up, in a sense. Used up meaning that they contribute to like the comfort of a cow. Does that make sense, that like general idea, and how you can maybe argue that this process will terminate relatively, like not in some egregious like n to the 15th, you know? Okay, cool. It's making sense. Okay, so we have some notion that that this will terminate fast enough. And so fast enough is like linear or whatever. Okay, so I guess the solution just seems like, okay, so it'll just straight up work, right? Like we have a solution. I guess like this bound is important because that's required to argue how long this will take, but it's linear, I guess, and so you can see that if you think about this argument. But okay, so this solution just straight up works, I guess, for our simplified problem. Remember, this is a simplified problem where we only are checking the entire n cows. So it's at this stage that we want to think about how do we now use this or modify things or think about how we can plug it into the entire solution. And we know that one thing we cannot do because of our conversation earlier is we cannot just apply the solution in isolation to each prefix, because that would be n squared. So I mentioned something about reusing information earlier on. And so that's where kind of like reusing information would be useful here, right? Where if you think about it, what actually changes when you go from a prefix to the next prefix? What actually changes when you go from the ith prefix to the I plus 1th prefix? What about the two problems are different? Let's see. You add one new cow. Exactly. Very simple. There's literally, it's a one cow difference. Okay. So the majority of the problem will be the same. All we need to do is figure out how to incorporate this cow, essentially, right? If we can figure out like how to incorporate this cow, then and kind of adopt it into our solution, then we'll be done. Any ideas here? And so actually here's a great point in time where maybe I can ask you guys like what is tricky, you know, like why isn't this super obvious of how we can just incorporate this cow? And the reason I'm asking is not because I'm saying you all are fools, you should know instantly what to do. It's because often in order to figure out what needs to be changed in the solution, you first have to know what is actually kind of blocking you. And so I guess what I suspect is that you're concerned about like, okay, what if this new cow is comfortable versus if it isn't? So what are kind of the cases here, I guess, is a better question. You know, like what are the cases of this new cow? And in what scenarios is it hard to handle this new cow? And what scenarios is it easy? So on and so forth. Okay, so good. So my issue is what if the new cow makes other cows uncomfortable? Yep. So this is a good point. So you can imagine a scenario where there was some comfortable cow last time, and so we've run our algorithm, and we let's say we like fill in this spot. But now Alex is raising the point. Well, what if in this next prefix actually there was already a cow here, right? So if there's already a cow here, but we placed one in the previous iteration, we actually don't need to place this one now because the next cow actually filled it in for free, right? So I guess here's kind of where we want to think about it. Okay, so how can we adapt our solution to handle this exact case? So this problem that we're running into is essentially the fact that we may think we need to do more work on the ith iteration than we need on the I+1th iteration. And so we kind of run into this problem of or I guess I don't really know how to directly say it, but it's like reusing work is a bit tricky because we may need to like also unreuse work. So here's where like a very common trick and technique is used, where without getting too much into the weeds of what this solution is actually like called or whatever, but it's like the idea is the problem doesn't require you to process these sub problems in increasing order, right? They want you to output it in increasing order, but you don't actually have to solve it in increasing order. So we see that we run into this problem when we go from the I to the I+1th prefix. But what about going in the opposite direction? What about going from the I to the I-1th prefix? Meaning we run the solution on the like ith prefix, and now maybe we can do something simple to answer it for the I-1th prefix. Maybe just check the new cow and the cows next to it. Sorry, is this idea for, can you explain this idea more, or what is it in respect to? If we're going in the reverse direction, like remember, there's no new cows anymore, right? Like we would be actually just removing cows. Okay, yeah. Yeah, so the trick here is to just remember that, you know, just because they want you to output it in increasing order doesn't mean you need to process it in increasing order. So why is processing this these prefixes in reverse order, why is that useful to us? Right? Like what actually happens when we go from like a problem with the ith prefix to the I-1th? Well, just like trivially, there's one less cow, right? But why is that so much better? Why is removing one cow so much easier to handle than adding one cow? Because we don't have to check the new added cow. Right. Well, there is no new added cow. Just to remember, right? There are no cows being added anymore. We're only removing cows, right? And the fact that we're removing cows means that, oh, okay, sorry, that is what you're saying, right? So in the forward direction, we would have to check a new added cow, but in the reverse direction, we don't have to check a new added cow because there is no new added cow. Exactly. So when we're removing cows, I guess the only thing we need to think about is if we were to remove a cow, then what happens, right? Well, let's just kind of think about this scenario where we've added this X is the cow we've added. We've added a cow, and now one of these cows gets removed. So what happens if one of these cows gets removed? Well, there's only 4 cows in this picture over here that could get removed, right? Because remember, the X is a cow we've added, and we'd only be removing original cows. So what happens if this like cow over here gets removed? So if this cow over here gets removed, then we don't actually need this X anymore because this original cow isn't comfortable, right? And the same is true for all of these other cows. If any of these cows gets removed, then we don't actually need this X anymore. So essentially what we can see is that the set of cows that we added, right, all these X's, the set of cows that we've added will like strictly be larger, or actually not strictly. It'll be like larger or equal to the set of cows needed to be added on like a previous prefix, right? So let's say like on when we have all n cows down, we may have needed like some set of cows, xi. sorry, I plus 1. But then when we look at like the n minus 1th prefix, then the set may be the same. Maybe we still need these cows because the cow being removed was already, like, it wasn't a comfortable cow. But in the case where it was a comfortable cow, then we don't need one of these anymore. And so this set will just become smaller. Right? So we see that in removing these cows, it's much easier to just check to see if a cow removed was part of like a comfortable cluster, then we can just decrement 1 from our answer, essentially. Right? Or like zero out this thing in our table. Right? And so essentially, if it's not clear about the full solution, then so essentially what we do is we run the solution that we described about doing this exploration, and like the official term for this sort of thing that we just did is something called a flood fill, right? Where we essentially, the reason it's called a flood fill is because, like, you can imagine pouring water onto the grid. So we poured water at like these red circles, and then like it floods out. In our case, like, it floods depending on this logic of, is a new cow comfortable or not? But that's why it's called a flood fill. So we do this flood fill on the entire problem, right, with all n cows, and then we just run through in the reverse direction and just do these checks as we start to remove cows, and just update the answer. Okay, so I mean, as we kind of see, like, problem may have been daunting at first, but we've kind of come up with a very simple solution here at the end. Maybe it's not so simple to implement because if you're not experienced with this sort of thing, like maybe there's some unclarity in how we can implement it, and we can maybe go over that at the end. But does the solution itself make sense, and how we got to the solution and the thought process? Yes. Okay. If it didn't make sense, ask now, or we can also revisit it at the end. But yeah. Good. Okay, great. So let us chat about the next problem now. Let me see. So the next problem was this year of the cow thingy. Okay, so in this problem, let me share my screen again. Okay, so in this problem, it's regarding the Chinese New Year and celebrating the 12-year cycle, which are these animals. And so essentially, in this problem, they say that a time portal opens up during the year of the ox, which allows cows to travel through time to any other year of the ox in the past or the future. Okay, so what does that mean so far? So essentially, like, if we have these yearly denotations, then we can jump 12 years back, or 12 years forward at any given step. Okay. So then they say Bessie the cow would like to take advantage of the time portal that is opened up this year to visit N of her famous bovine ancestors who lived long ago in history, with N being bounded by this hex number, which they tell us is this number in decimal. We can just call it 10 to the 5. Okay, unfortunately, time travel makes Bessie a bit queasy, and she would prefer to make at most K jumps through time. Okay. Please have Bessie determine the minimum number of years it will take her to visit all of her ancestors and return to the present year with the most K total jumps along the way. And then the rest is just like some not important thing. Okay, great. So does anyone have questions about what this problem is asking us, first of all? All right, cool. So let me pull up the whiteboard again then. Alrighty. So, and I'll just recap it anyways. But essentially, we're given these. You can imagine a really long number line in history, or I guess a timeline, right? And let's say maybe we start here, and this is like the year of the ox. And so every 12 years, there's like these year of the ox segments. And essentially we can make jumps to any of these times. Now, in addition to these year of the ox segments, Bessie has ancestors that may live at these red lines. It could also be in year of the ox, may not be. Or I forget if they say only back in time or also forward. It says long ago in history, but I guess they don't really say what year we start at. So you can imagine it's also forward in time. Yeah. Wait. Time portals connect the first days. Bessie starts her adventure on the first day of the present ox year, so she can travel back in time. Oh, okay. So they also say none of her ancestors actually live in ox years. So this is not possible. Okay, great. Okay, so sorry. So I guess we don't really have to worry about this notion of the future compared to where Bessie starts. So I can just make Bessie start over here at the first thingy. Because in the input, the numbers they give you are all positive numbers, and those are just how many years previous to, like, in history are the ancestors. So in the sample input, they give 101, meaning there's an ancestor 101 years before today, which is where Bessie starts, so on and so forth. Okay, great. So essentially what we want to do is we want to basically select some number of jumps, right? And we get k jumps in total, such that the minimum number of years it takes in total for Bessie to wait. And so essentially what Bessie can do is if she jumps in this ox and she waits for 12 years to get to this ox, then that counts towards the answer. But like any jump doesn't count. Like this doesn't count as 12, 24. This doesn't count as a 36-year like thing in history, right? We've used a jump, so it's free. And so the idea is to minimize the total yearly wait time. Okay. So does anyone have any questions so far about what this problem is asking? Okay. So let's what are maybe some initial ideas or thoughts? Does anything jump out in this problem of like what we should kind of do? Okay, and I see that there's a chat. Can you only jump backwards? So that's a good question. So no, you don't have to only jump backwards. I think it says, and you guys should all pull up the problem statements on your own as well, so you can double check. Reading the problem statement carefully is very important. I believe it said somewhere that she can jump forward. So let me see. Did someone check? Okay, wait, let me see. I want to make sure that we're doing this right. Yeah, okay. So it says at the end of the second paragraph, slightly lesser known is the fact that time portal opens up, allowing cows to travel through time at any other year of the ox in the past or the future. So she can jump to the future. Okay, so Keshev said, maybe something to do with how close each ancestor is to a year, which is a multiple of 12. And then Winston says, I think you can jump back to where you started. Oh, sorry, Winston, are you replying to Alex in terms of you can jump back to where you started? So yeah, so okay, yeah, you are. Okay. So yeah, you can actually jump forward to any time portal, any ox time portal. You can go in either direction to any ox time portal. Okay. So Keshev kind of had this idea of maybe something to do with how close each ancestor is to a year, which is a multiple of 12. Okay, and so what's kind of the motivation behind this idea, Keshev? Like why would this be beneficial to think about, or like, or what's kind of the intuition here? Because we can minimize certain things. Yeah. So definitely it's kind of a good idea because Well, we want to leverage the fact that we have these free jumps. Like we can wait a certain amount of years. Okay, great. Yeah. So we have this ability to jump back. And so Keshev is basically saying that, Keshev is basically saying that when you jump back in time, you want to pick up some ancestors. So I guess like how can I explain this? So okay, so let's say that we have two year of the oxes here, right? So this is the first year of the ox. This is another one. So essentially, what we can do with our time jump is we can either jump from somewhere back to here, or we can jump back to here, right? So obviously, we don't want to jump back to this place, right? And the reason why is because, well, there's no ancestors here to pick up. Remember that once we go to a point in time, we wait and we move in the forward direction, right? We can't wait and go back in time, right? So so Keshev is basically saying that we want to look at these ancestors that are very close to multiples of 12. So for example, these two ancestors right here, they're close to this year of the ox. So we want to jump to this year of the ox to basically save 12 years of waiting that we would have just done for no reason if we jump back to this previous year of the ox. So that's definitely a good intuition there. Okay, so maybe we can imagine that we want to carefully choose which years of the ox to jump back to. And we'll do some jump and we'll do some waiting. And then after we do any waiting, of course, we can just choose which other segment to jump back to. So maybe our algorithm looks something like and let me also draw this. So maybe our algorithm looks something like we jump here, we wait 12 years, then we jump here, and then we wait. And actually, we don't need to jump again. So we can like pick up these, and then we jump here, and then pick up this, and we can pick up both of these, etc. So on and so forth. Okay, so, oh yeah, and Alex said something. Seems like if there's a birth between two ox years, at some point we have to travel through those 2 years. Definitely. Definitely. So Alex made a good observation that if there's a red thingy, essentially between any two black poles, then we will necessarily have to travel between those two black poles, right? And the reason behind this is because, well, in order to actually get it, you can only like time travel through the 12-year poles. So whether or not you decide to jump into one of these starting points, or if you decide to just live through time through one of these starting points, you'll always go through the pole right before the red ancestor and the pole right after the red ancestor, whether you're continuing or you're jumping. Okay, so Keshev's also saying, go through the portal, then wait that amount of years to get all the ancestors. Yeah, so yeah, exactly. So this is kind of the initial algorithm that we just came up with, right? So essentially, choose the closest time portals to jump to that are before some ancestor, and then just continue going until there's no ancestor to pick up in the next segment, and then make your next jump. So essentially, you want to just like skip out over these blank sections in history. Okay, so this is all well and dandy, but there is one problem. So there's one reason why this algorithm doesn't fully work. And I guess not in terms of correctness, like it's certainly correct, but in terms of what the problem's asking. Anybody see what we haven't considered yet? We need the minimum. Okay, well, yes. So sorry. So to be more pedantic about this actual algorithm that we've just discussed, is we would be choosing these jumps. Okay, so actually, how can we argue that this algorithm does give us the minimum? So if we are jumping, so just to be very clear, our algorithm is take jump to the closest portal before any ancestor, and then just like wait through the year and then make the next jump. So why does this algorithm necessarily give us the minimum answer? And so a good way to argue these sorts of things. So I guess, sorry. Okay. Yes. So Alex raises a good point, but so that is the point I was talking about. But really quickly before we hop into that, just in terms of arguing why this algorithm does give you the correct, well, this algorithm would give you the minimum, but we've made an assumption, and that's the assumption Alex just mentioned. We've made an assumption that we have infinite jumps. So if we do have infinite jumps, then this algorithm will give you the correct answer, because you can use something called like an exchange argument. So this algorithm that we've described is a greedy algorithm, where essentially we're saying it is always optimal to jump to an aux year that is right before an ancestor, right? And so the exchange argument is basically that, well, if it isn't, then or like, let's say you claim that it's actually not optimal to jump to one of these things before, such as you should, instead of jumping to, let me draw a different color. So if someone was like, it's actually not optimal to jump here, it's instead optimal to jump here. Well, you can just do the argument that we just said about, well, actually it's not, because if you tell me it's optimal to jump here, there's no ancestors here. So I will just skip that and jump to the closest one before. It's a very simple exchange argument in this case. But that's why this algorithm would in fact give us the minimum. However, we're not taking into account the fact that we only get k jumps, right? This algorithm would give you the minimum if you get as many jumps as you want. And let me read now what this says. So the best solution is to back to the farthest necessary year and measure which jumps between necessary years save us the most and subtract that. Okay. Yeah, exactly. So Alex has come up with the correct solution here. So the thing that we need to figure out is, how do we factor in this k to our answer? So we see that we can, let me modify the example a bit. Do I have eraser on? Oh yeah, I do. Okay, so let me drop this. But yeah, okay. So you kind of see here in the diagram that there's like segments of time that don't have any ancestors. And these are the segments of time that we want to avoid. But as people have pointed out, since we only have k jumps, we have to pick and choose which one of these segments we can avoid. Because the jump allows us to like skip over these long segments. So we only get to avoid k of these. And we know that we need to arrive at these like key kind of boundaries, right? And we get to skip over certain things. So the idea here, which Alex said, is basically all we do is we look at all of these boundaries, and we just do the greedy approach where we skip over the k largest gaps, right? Because if we were to actually wait in time through these gaps, then that would be the most expensive. So it's always optimal for us to skip over these largest gaps and only, and if we run out of jumps, then we only have to now wait through the smallest gaps. And there's no way around that because we only have k jumps. Does that make sense? Kind of how that algorithm works? Okay, so what's the complexity of this solution? Any ideas here? Right, so the first thing we have to do is basically find, well, there's two things that we have to do, right? We need to find, like this notion of gaps is something we've created, right? In the input, they only give us the year and time, like they give us the red lines essentially. So what we want to do is we want to calculate these black lines essentially, and we need to calculate these green gaps because that's where we want to skip or not skip, right? So I guess it's more of like an implementation exercise at this point. But in order to actually calculate, well, calculating where the black things is very simple, right? Because you just take the closest multiple of 12 to a given number. But then you have to calculate these green gaps, which might be a bit trickier. But then we want to pick the largest, the k largest of these gaps, and so we can do that by just sorting our list of gaps, and then just running through the list, right? So overall, it's an n log n solution because we have to sort, and there can be at most k gaps, or sorry, n gaps. So yeah, and we're sorting this list of gaps. So it's a pretty efficient algorithm. But yeah, okay. Any questions about this? Okay, cool. Let's move on to the last one. And I think the last one's the hardest one. So it's good we have some time to talk about it. And then we can vote or something on what to implement. All right, let me share my screen again. Okay. So this problem, we're given another grid. This time it's not an infinite grid, it's a fixed grid. So it's a 500 by 500 grid. And each cell here has some grass, and each cell has a level of greenness of grass, which can be anywhere from 100 to 200. Now, Farmer John wants to take a photograph of this pasture, essentially a subgrid, right? Like a rectangle. He wants to just take a rectangle of the whole grid, and he wants to make sure it looks green enough, but not too green. So the way he decides this is he decides to, or like a feasible photograph is one that has a minimum value of greenness of exactly 100. So, and they basically want us just to count how many possible grids can he take a picture of that are valid. Okay. So any questions about what the problem's asking? It's kind of a simple problem to understand, not so simple to solve. Okay. So the first thing that maybe we want to think about is what does it actually mean for a rectangle to be sufficiently green? So they gave us this jargon about that they want the minimum value of G to be exactly 100. So they want the minimum value of G to be exactly 100. What does that actually mean in a rectangle? So in a rectangle, if the minimum value of G is exactly 100, what does that mean about all of the elements in the rectangle? Any ideas? So you can say something about each element in the rectangle in a validly green rectangle. Okay, so maybe this is just a dumb question to ask, but basically, like, the idea is if the minimum value is 100, then all the elements must be at least 100, right? That's essentially what it's saying. So we want to be looking for these rectangles that have minimum value at least 100. Okay. So does anyone have any ideas on how we can kind of start solving this problem? Or like if you've already thought about it, or you tried it in contest, what were some ideas that people had? All right, there's an idea. When getting the input, we could modify it so we know which values are less than or greater than 100. Okay. So yeah, so we can kind of think about which elements are less than or greater than 100. Why does this help us, Keshav? Or why would we want to do this? or anyone else as well, why would we want to modify the input to know if a value is less than or greater than 100? To build on Keshav's idea, we can simplify the numbers to -1, 0, or 1, which means less than 100, 100, or more than 100 respectively. I guess it would make it easier to code. Okay. Yeah, so that's not a bad idea. So I guess what I'm getting at is what you want to think about is with any one of these ideas is it an implementation trick or is it like a thinking trick? And so what I mean by that is like there's some things that make it really easy to code. So like for example, when doing a flood fill, let me just type this out here. So when doing a flood fill, one implementation trick to explore your neighbors is to create like a dx and dy array, right? I don't know if people have seen this trick before. Did I do this right? No, I didn't. Did I do this right too? Yeah, okay, I did this right. Okay, so here's like an example of an implementation trick. So you have this dx and dy array. So let's say I want to get all of the adjacent cells to me. Well, what I can do now is I can just run a for loop through these arrays. And let's say like my current y or my current x is like 3 or 2. And my current y is 3. Then to get all candidate like neighbors, like new x would just be cur x plus dx of I. And this gets me all of my adjacent cells in a very succinct manner, right? And so we can think about this trick in particular and why it works. So let's think about what the dx and dy is actually doing. Well, what it's doing is it's literally just it's just like adding and subtracting the right values and the right coordinates to get my adjacent cells. So like, let's say I'm like right here. And sorry for this aside, but I think it's a good thing to know if you don't. Let's say I'm like right here. Well, let's think about what each index of this array of these arrays do. So this first index basically tells me my change in x is -1 and my change in y is 0. So what is that cell that's -1x and 0y? Well, it's right here. Then the next one says my change in x is 1 and my change in y is 0. So where is that? That's right here. Next one says change in x is 0 and change in y is 1. Well, that's right here. And then -1 right here. Right? And so that gives you all your adjacent cells. So that's an example of an implementation trick. Now, an example of maybe an example of like a thinking trick is a bit harder to see. But essentially what I'm asking you is, so you mentioned like this might be easier to code. Well, is it just that? Is it just easier to code? Or is there a reason why this transformation would help us to actually solve the problem? Does that make sense? Kind of the distinction of what I'm asking? Okay, cool. Oh, also, yeah, before we move on, did anyone have any questions about this dx dy thingy? Does everyone get how it works? I think it's pretty cool. Okay, assuming everyone's good with that, then. So back to the problem. So back to the problem, we're considering this this idea of like transforming the data to be 1, 0, or -1, depending on if a given number is bigger than, equal to, or less than 100. And maybe we don't have any idea of whether it's useful or not. Maybe we just thought of it and then we're not sure how to proceed, which is also completely fine. Let's just assume that we just thought of it. We're not sure if it's actually helpful or not. Um, okay, so what other ideas do we have? So I guess what would a brute force on this problem look like? It's always a good place to start if you have absolutely no ideas of how to approach the problem. Check all subgrids. Yeah, exactly. So what would that look like? So just checking all subgrids. So the first question is, how many total subgrids are there? Yeah, okay. So let me pull this back up. So someone in chat gave some nasty expression, which is correct. So I guess in general, in computer science, we're lazy, and so we don't like doing real math. So the expression that you gave simplifies in big O notation to just n to the 4. Right? So we'll just call it this because it doesn't actually matter. Computers are fast. We don't have to worry about the constants. Okay, so n to the 4. So do you want to explain where this number came from? I forget who said that. Keshav said it. Do you want to explain where this number comes from in chat or vocally? Oh, it's in the problem statement. Oh, it is in the problem statement. Okay, well, let's think about why this is the case. Does anyone have any ideas of how to actually like come up with this number? It's like n times n plus 1 over 2 squared. Okay, so why where is this n times n plus 1 over 2 squared coming from, Winston? And why is that squared useful? I forgot what it was for, but it was something to do with choosing. Yeah. So okay. Yes. Yes. So this is all right. Like technically, yes, it is all about like choosing or combinatorics or combinations and whatnot. I don't want to know like the math. I want to know the reasoning, right? You can't just produce a mathematical expression and be like, oh, this is the answer because that's how probability, or you can't just like argue like, what is the reason behind the expression? That's what I'm asking about. Like basically you're just telling me that n choose 2 is this, which is correct, but I mean this is just a math fact. This isn't telling us. Yes. Great, Winston. So Winston says it's because you have to choose the start point and the end point for the length and the width. Yeah, so if we think about a rectangle, right? A rectangle is defined by its endpoints, or sorry, not its endpoints, but by its like actual coordinates of its corners, right? That is all you need to define a rectangle. So you can either have like the 4 corners, well, so you don't actually need the 4 corners. So this is actually some duplicate information. All you need is 2 opposite corners. 2 opposite corners to define a rectangle. But one nuance here is having the 2 opposite corners still gives you 4 pieces of information. Right? It gives you like 2 x and y coordinates. Okay, so all you need to define, so we can just think about it in terms of corners because that is what the 4 piece of information is, right? So all you need to define a rectangle is just know where each corner is at. Okay, and so essentially to think about all rectangles that might live on this grid, well, we can just move each corner, right? So let's start a bit simpler and just think about what is the number of rectangles that start in the top left corner. So let's just fix this top left corner and then draw like some rectangles. So like this is one rectangle. This is another rectangle, right? This is another rectangle, so on and so forth, that all start in the top left corner. So how many total rectangles are there like this? Well, there's a total of n squared, right? I think it's kind of easy to see because essentially what we're doing is we're just taking this bottom right corner, we're dragging it around this box, right? And so there's a total of n squared possible locations this bottom right corner can be. So that's where we get this term from. And in particular, it's n choose 2 because if you want to be very nuanced about it, right? Like not all of these things are actually possible. Or I guess in this case, it's because they don't want so they're not including squares or what is this? So I guess yeah, this actually. Yeah. Okay. So ignore this for a second. Here, a better example is here. So let's say now we're starting to move the top left corner as well, and we're trying to place these rectangles everywhere. Well now, okay, I'll explain where this comes from in a second. But like, well now we also can move the top left corner. So now we can move both the bottom right corner and the top left corner, and each of these can go anywhere. So there's n squared locations for the bottom right, and there's n squared locations for the top left. So that's a total of n to the 4. But as you can probably imagine, we're overcounting a bit if we say it's exactly n to the 4. And the reason why is because, like in combinatorics, for instance, or like when we do n choose 2, this is essentially just like choosing each coordinate. And so like if I chose, there's like some degenerate cases here, I guess. Like if we're fixing this to be the top left corner, then like, for instance, this cannot be on the right of the bottom left corner, for instance, right? Like there's some edge cases here that if you want to actually carefully count it, it is the expression they gave. But it's not important for our analysis, right? Like it's just n to the 4. Okay, so there's n to the 4 subgrids in total. So going all the way back to where we came from, this was all just to discuss what the brute force solution would look like. So we iterate over all n to the 4 subgrids, and then what? And then we just check them all, right? And so how long would it take to check a subgrid? The size of the subgrid. And so in big O notation, in the worst case, how long would it take? N squared, exactly. N squared. So there's n to the 4 total subgrids, and it takes n squared to check each subgrid. So the most naive of naive solutions would take n to the 6. Okay. Okay. So for n is equal to 500, which they gave us, this is way too slow because n is equal to 5 times 10 squared. And this is actually, I don't even know how big 5 to the 6 is, but 5 to the 6 times 10 to the 12. This is probably something like, I don't know, like 10 to the 14 or something, or even bigger, 10 to the 15. Okay, so this is rather large. So I will say now that there's a common technique that you can actually go from this complexity to this complexity with like a very small change, like a very simple speed up. And this is actually very often used in a lot of problems, so it's a good trick to know. And I'm not actually sure the subtasks. Oh, okay, so they give you a subtask with n is less than 200. So n is less than 200. So if n is less than or equal to 200, maybe this solution gives us something. So if that's the case, 2 times 10 squared, if you do n to the 4, it's 16 times 10 to the 8. Okay, so we can actually get the first subtask if we come up with the n squared solution, or n to the 4 solution. right? This will pass probably. 1.6 times 10 to the 9 will probably pass. So does anyone see how we can easily get this n fourth solution still doing a brute force fashion? Okay, good. So I'm glad no one knows this. So this will be a good thing to cover. So essentially, I guess maybe the theme of the day, you can argue, is reusing work, right? So if you imagine, a lot of these rectangles will just be like slight perturbations of like another rectangle. And so one example of that is this blue rectangle down here, and then like the next rectangle. If you imagine we were generating these in some order, the next rectangle might just look something like this, right? So the idea here is to use some kind of sliding window technique where you don't actually need to recompute a lot of information as you go from rectangle to rectangle. And so the idea here is basically, as I'm like moving across and generating these rectangles, I'll just be doing the check as I go, right? And so if my check is like making sure that there's like a minimum, the minimum is at least 100, then I can just do that check as I generate the rectangle. And actually, wait, maybe I lied here. Maybe it isn't just n to the fourth trivially. But the general point still stands. I think you can get it down to n to the fourth with some additional pre-processing. But just for time's sake, I'll just cover the one-dimensional case, and you can expand it to the two-dimensional. So let's say we were just doing this in 1D, and we were doing all of these segments instead. So there's n squared total segments, and I'm basically claiming that. So there's n total segments, and if we did the brute force check where we checked each of these segments can be n long. So that's a total of n cubed. But I'm claiming that you can actually just do it in n squared if you pre-process carefully. And so here's the way to do it, right? So the two things we're moving are the start and the end in this scenario. So let's say my start is here, and I'm gonna like put my end here, and then I'm gonna move it over, put my end here in the next position, so on and so forth. And I'm gonna like start here, move all the way to the end, right? And then I can advance my start and then go back and move all the way to the end, so on and so forth. So what we can do here is what we can just be computing the answer as we go to the right. So let's say we're just fixing the start, and we're sliding the end segment along. Well, what I'll do is every time I slide it along, I'll just check, is this element less than 100? If it is, then what do I know about this element and actually everything after it as well? We can't use them. Exactly. They're invalid. So I can do the check as I brute force over each segment, and there's really no need to go and redo all of the work. Because if this segment works from the start to here, if this segment works, then all I need to check is the next element. Because if this works, then if the next element works, then the entire segment works, right? And so I'll be calculating the answer as I go along. And so you just have to be sure that you're processing it in the right way. So the order is like, I'll fix my start, I'll do my end, and then I can move my start along and then keep going. Does that make sense? How just processing it like this, how counting as you go shaves off a factor of n? And you can argue it's probably actually easier to code as well. Right? Does everyone understand this technique? And then you can apply it to the n squared by yourself. But very, very important technique. Shows up everywhere. Okay. So that's just like a cool little aside. And so I think if you're careful about the way you do the processing and storage of stuff, then I think you can do n to the fourth. It seems possible. Okay. So regardless, this isn't going to give us the full problem, and the point of this is to get the full problem. But yeah, so we kind of have like a brute force here already. we just want to do, we just need to figure out how we can speed this up. And so the first thing that we know is that even going over all of the subgrids is too slow. We can't even go over all of the subgrids. And so essentially we want to think of like, how can we save even more work? How can we save even more work? Yeah, so take a few more moments and just think about this for a bit. Only look at the subgrids with 100s in them. Yeah, so this is very interesting. This is very interesting. So only look at subgrids with 100s in them. Okay. So I guess the tricky thing here is so push on this a little more. So what do you mean by only 100s in them? So like, surely there can be like valid subgrids include subgrids that don't have hundreds in them as well, right? But which numbers that don't have 100s in them? Was that clear what I was saying? Right? Like certainly subgrids that only have 100s in them will be valid subgrids, but there's more subgrids as well that don't have hundreds in them that are valid. But what numbers are these? Other numbers that are allowed to be included? Numbers greater than 100. Exactly. So we're allowed to have numbers greater than 100 in our subgrid as well. So we want to look at these rectangles as well. So this is actually going back to the first point about like this whole, like, is it an implementation detail or a thinking detail? And so I think kind of what we've seen here is actually it's a thinking detail where we don't actually need to worry about like the -1s or the zeros, but we can just have like these valid numbers that are allowed to be included in any subgrid, and we can define them to be like the ones in our table. So let's define an element to be like 1 if it's greater than or equal to 100. Right? Let's define an element to be a 1 in our grid if it's greater than or equal to 100, and 0 otherwise. If it's greater than or equal to 1, then it's equal to, or if it's greater than or equal to 100, then it's equal to 1. Okay, so now let's think about counting these subgrids. But before we do that, let's think about, is this if we're able to count the number of subgrids that only contain 1s, is that the correct reduction of our problem? Like, does that actually solve the original problem? No. Kashyap says no. Cheryl says no as well. Why not? Because greater than or equal to 100, we can't distinguish the 100 from the other numbers greater than 100. Cheryl says there's ones where it's more than 100. Yeah. So the idea here is that, remember, the problem was really annoying, and they said that we needed the minimum to be exactly 100. So if now we're only searching over these ones that include numbers that are greater than or equal to 100, we may be counting subgrids that have numbers just greater than 100, and it doesn't have 100 in it. So the minimum isn't 100, it's something bigger than 100, which is unfortunate. So clearly the solution won't give us the correct answer. So we need to think about how we can handle this. So in this version of the problem, we're overcounting, right? Our answer will be overcounting. So one way that we can not overcount is to just subtract the stuff that we overcount, right? This is like, simplistically, it's like an example of complementary count. Well, it's not really complementary counting. It's like inclusion exclusion is more of like the term. You're including some answer because it's easy to count, and then you're excluding like the invalid scenarios that you counted because it was convenient, but it's not actually part of the answer. So we want to, so if we count on our problems currently, the number of subgrids that are all ones with this transformation, then we want to subtract out what kind of subgrids. What do we want to subtract out? How would you define what we want to subtract out? Right. So in this problem, like the exact subgrids that we're overcounting are those where where we're counting like a rectangle of all ones, but none of those ones include 100. Right. So the rectangles that we want to be subtracting out are those rectangles. The question is, how do we, like, we can either come up with another solution to subtract this, or there's a neat little trick that we can use to easily subtract this. Does it make sense, first of all, which subgrids we're overcounting? Like maybe I'll give an example. Like let's say prior to the reduction, this is like 100, 101, 112, God, 105. And then let's say that this is like 111 and 200. Right? So after we do the reduction, it looks like 111, 11, and zeros everywhere else. So what is a valid rectangle? Well, one example of a valid rectangle is this. So we'd count it. Great. We're not missing anything because there's 100 here in this rectangle, right? So the minimum is 100. Now, what's an example of an invalid rectangle that we would count? Well, it would be a rectangle like this, right? Because there's no 100s here, right? They're all greater than 100. Let me actually change this number. Right. So does everyone, first of all, just so we're all on the same page, everyone sees what the problem is with this reduction. Okay, everyone sees what the problem. Great. So essentially what we want to do is we want to make sure that we're still counting all of these red guys, but we want to not count these orange guys. But instead of not counting these orange guys, we just want to subtract them out. So we do want to count them. We're also going to count them, but we want to count them separately. So essentially in this current reduction, we'd count both the red and the orange. We want to come up with another reduction that'll count only the orange. And then if we subtract them out, then we have the right answer. Right? So that's the whole idea behind inclusion exclusion. So does anyone see what this reduction is going to be to only count these orange circles? Or yeah, these are like orange subgrids. And it's very, very similar to the format here. In fact, it's one character different. All right, for the sake of time, I'll just go ahead and share it. So the other, yeah, exactly. So Keshav got it. The 100 and greater than 100 have to be different numbers. So like the next reduction we'll do is greater than or equal to 101 equals 1. So why does this help us? Why does this only count the orange? Well, if I now go ahead and write what the problem will be after the reduction, it'll now be 0, 1, 1, 1, 1, 1. So in this new problem, note, we would not draw this red circle because this is no longer valid. We would only draw this orange circle. So in this other reduction, now we're only counting the oranges, and then we can subtract them out, and now it'll be only the reds, and this will be our answer. So it's a pretty nifty trick, right? And it's like the same school of thought as like the idea of prefix sums. I'm assuming you guys are probably familiar with prefix sums given you're in silver, but if you're not, it's not a big deal. You can learn about it later. But if you are, just really quickly, like the idea of prefix sums is it's in order to do any sort of range, right? You always just take, if you can answer a query of count the number of things that are less than some number, or count the number of things that are greater than some number. If you can answer any kind of query like this, then you can also answer a query where it's within, like within some range, right? If you can answer one end of the range, you can always answer like a two-sided range because you just subtract out the extra, right? So prefix sums are like, I'm answering what is the prefix from the start to me. So I can answer any range because I can just ask the same question here and just subtract them out, and then I have the difference. And so that's the same idea here, right? We're answering it where it's greater than or equal to 100, so we can just ask the same question for another thing and then subtract it out. But regardless, so let's forge ahead because we're already running close to time. Okay, so so now that we have this reduction, we can completely throw out this worry about the orange and the red, and we can just focus on, we want to count the number of ones, of rectangular ones, all ones, right? We've now reduced the problem to this. We just want to count the number of all rectangular ones. Right, so maybe there's ones and zeros, and we just want to count the number of subgrids that are all ones. Okay. So once again, I recommend looking at a one-dimensional case because generally, whatever, like if you can come up with a 1D case, you can usually always extend it to a 2D case just by adding a factor event to the complexity, essentially. So what would this look like in the 1D case? Well, I have like a bunch of ones and zeros interspersed, and I want to count the number of segments that have all ones. And I want to do this, I guess, I need to do this in linear time, I guess, or just like as fast as possible. We can think about how to do this as fast as possible. So any ideas on how we can answer this question of, I want to count the number of rectangular one subgrids. And so maybe one thing that you can be thinking about is like, in order to make this faster than n squared, like I can't look at every single range, every single segment, right? So let's think about what rectangles will contribute to the answer. Well, we know that anything that has a 0 in it won't contribute to the answer. So like this will, like this stretch will contribute, this stretch will contribute, this will contribute, so on and so forth. Any rectangle that, or sorry, any segment that like crosses any of these segments will not contribute to the answer. We don't have to consider them, right? So the question basically becomes, we need to count how much will each of these segments contribute to the answer. And there's a way to do this in O of 1 time, like for a given segment. Does anyone know like how many rectangle or how many segments each of these red underlined segments will contribute to the answer? Okay, so for the sake of time, I'll just go ahead and say it. But like, you can imagine each one of these segments, since they're fully ones, since they're all ones, you can have a start and end anywhere in between them, right? And so to avoid for overlap and whatnot, it'll just be, let's call this X. Let's call each of these sizes Xi, these runs of 1. Then it'll just be Xi choose 2 for each thingy, for each segment, right? And so Xi choose 2 is just X as we wrote out earlier, each run will contribute this much to the answer. So then what is like the total answer? Well, the total answer is just this expression summed over all i's, where i's are like defined as each run. So the problem now boils down to we need to find each run of consecutive ones, figure out the size of each of these things, and then just add this multiplication to the answer. And hopefully this doesn't seem too challenging, right? Because how can we do this? I'm just going to go ahead and forge ahead. Sorry, I can't pause it. If you have the solution in mind, then good job. But essentially, we just need to run through this, and we just keep a running counter of how long is our current set of ones, right? So like if my current element is a 1, I'm like, okay, add 1 to my current run. If the next one's a 1, add another 1 to my current run. I hit a 0, so I'm like, okay, I'm at the end of my current run. What is the total number? In this case, it was 2, so I do this math and add it to my total answer. If the next one's a 0, then I just do the same thing, right? Okay, I hit a 0, my run was 0, I add 0 to my answer, so on and so forth, until it's a 1, and then it's like, okay, now I can reset my current run, and I don't add it to the answer yet. I'll only add it if I hit a 0, right? Because that means I've ended a run. So now I have 1, and then 2, and then 3, and then 4. I hit a 0. Let me add the math to my run. Okay, so that is this simplified version of, okay, so now we can solve this problem in linear time, right? Notice this is a linear time solution. We're just running through this one time. So we can now solve this problem in one dimension. So now the question is, how do we extend this to a two-dimensional problem? And so I guess the idea will be relatively similar. You basically just need to figure out how can you define these runs in one dimension, right? And then sweep in the other direction. So you can imagine, like, I want to like define some list of runs like in a vertical direction, right? So like this is a run in the vertical direction. This is a run. This entire thing is a run, right? So I have like these vertical runs, and then you just need to figure out how can you like then just combine them in the horizontal direction. And I know I'm leaving this vague intentionally because I think this is a really good problem to work through on your own. Like if you can figure this out, then you should feel really good. But are there any questions up to anything we've done so far? Like obviously excluding this, how to extend it to the two-dimensional case. And also, I guess if you took silver in December, there was another problem where essentially it was like extending one-dimensional prefix sums to two-dimensional prefix sums. So if you haven't done that yet, you definitely should as well, right? Any kind of like one-dimensional thing, extending it to 2 dimensions is a great exercise. That really makes you a much better thinker and coder. But are there any other questions around this problem? How we came to the answer, the general technique, right? So after you extend this to the 2-dimensional problem, you're just done, right? That's the whole solution then. Right, and you need to make sure you do it in n cubed time, right? Not into the 4th. Okay, so if there's no questions, I guess we're technically like over time, but I'm trying to think, how do I want to do this? I guess do people have any specific questions about any implementation, about their own implementation? I don't want to say that I have enough time to do a whole problem, but I can maybe try at least implement a part of something. Or is there any like popular request about how to implement something we've talked about, or if people struggled with something when they're implementing, anything like that? Okay, so I guess like we're technically done then. If people do want to stay after and ask specific questions, I can stick around for a little bit. But yeah, thanks everyone for coming, and hope this was informative.
Thank you.
Yep, for sure.
Thank you.
No problem. Alrighty.